Good morning, physics students, and welcome to another edition of Physics. It's Mr. Finn coming at you again from neighborly Northville. Hey, this is a shout out to my honor students. Hey guys, this is actually just a filler video for the segments of magnetism that include the previously recorded videos. I mentioned in a previous video that you guys were going to have some videos that were either previously recorded or moved over to your class from the regular class. However, there's a couple of additions. So I'm going to go through those in just a minute. But first, the dates we have stuff hasn't changed. We still have Wednesday Google Forms. Those are 3 questions. We have a Friday Google Form. Those are 10 questions. And we usually have a simulation or activity during the week. Google Meets for you guys are still on Thursdays. Secondly, for the magnetism section, that's section dealing with chapter 20, you only need to be responsible for 20-1 through 20-7. The rest of the chapter really is complex, and you're going to save that for AP Physics if you guys are moving on. So simply 20-1 through 20-7. And I'm going to go through a couple of those things as we hit the board, magic board. But before we do the magic board, I want to talk about something you're going to get from the video, if you've already seen it, from Dr. Jerry DiNardo, or Bruce DiNardo, of the Naval Postgraduate School. We have a charge moving across our screen. So let's say we have a charge. This pen is a charge moving across my screen. Let's say it's a positive charge. And it's going to enter into a magnetic field. The magnetic field is going to point out towards you, the viewer. So a positive charge moving into a magnetic field pointing out. Using my right-hand rule and the idea of the fundamental magnetic force law, which is QVB, sine theta if you're not a maximum. But here's my positive charge coming in. My magnetic field goes out towards you, the viewer. So you must move your right hand in the direction of the moving charge, curl your fingers toward the magnetic field, stick out your right thumb. The right thumb, or the right-hand rule in this case, points in the direction of the deflection, the force of deflection on the moving charge. So this charge positively would enter into a magnetic field pointing out at you. The right-hand rule would say that the force of deflection would be up, and therefore your particle would go up. If it was a negatively charged particle, the effect would be the exact opposite. So even though you put a force of deflection this way, the force of deflection for an electron would actually be downward. So you guys are going to need that when you get into questions 7 and I think 9 or 11 in the homework problems. No problem, guys. It's a fairly simple concept. Just follow the right-hand rule, fundamental magnetism, Dr. Bruce DiNardo. Now, what about if it's around a wire? Or what about this magic magnetic field surrounding a wire just to begin with? Well, for that, let's go to the magic board and we'll address some issues there. Okay, guys, here at the whiteboard, let's take a look at some of the things you've got coming up. Number 1, the definition of magnetic field around a wire. Now, if you're going into AP Physics, we'll actually go into this more detail in that class. But for us, let's just talk about the result of that derivation. It's mu naught rather, times I divided by 2 pi r, which has to deal with the radius away from the wire. So, if this was a wire carrying a current in this direction, by the right-hand rule, there would be a magnetic field surrounding this wire circularly. That magnetic field would diminish in its strength the further you got away from the wire. So any overhead power line carrying charge has its own magnetic field surrounding it. That magnetic field diminishes as you get further and further away from the wire. But haven't you ever noticed how weird it is that trees grow away from the power lines? I wonder if there's something to trees growing away from magnetic field strength. But either way, mu naught though, this is not 48 times 10 to the negative 7th. It's 4 pi times 10 to the negative 7th. And the units are Tesla meters divided by amps. Okay, so guys, that'll end up then. The vast, the net result of B, it will be in the units of Tesla. So again, what is mu naught? It's actually the magnetic permeability of free space. Remember, we have permeability of free space too with electric fields, but we have one for magnetic fields as well. And it's 4 pi times 10 to the negative 7th. Mu naught. Okay, guys, so from Dr. Bruce DiNardo, he mentioned that the fundamental physics, or fundamental magnetic force law, was QVB at maximum. That would mean at 90 degrees. If you're not 90 degrees, that would mean it'd be QVB sine theta. In other words, the force of deflection would be charge times the velocity of the particles, the velocity of the charge's value, times the magnetic field strength that it enters. Now, if it's not 90 degrees, you got to take the sine of the angle between the velocity of the moving charge and the magnetic field, those vectors. But for wires, it's actually ILB sine theta. You may be asking yourself, well, why is it different around wires? It's actually not different if we take a closer look. ILB sine theta, what is the definition of I? It's charge divided by time, Q divided by T. And if we play around with a little commutative property of multiplication, we can see that we could represent Q by itself and move this time component to be underneath the length. So length divided by time is simply velocity. How far something is in how much time represents a velocity. So charge times L divided by T, which is the same thing as V, times B sine theta. So ILB sine theta for wires is really the same thing as QVB sine theta. Dr. DiNardo, thank you so much. The fundamental magnetic force law. Fantastic. Okay, guys, I hope that helps. Let's wrap up here. Okay, guys, I hope that helps as you navigate through the beginning parts of the magnetism section. Now remember, we're only 20.1 to 20.7, so there's really just a few main concepts, really about charge entering into fields, about the interaction of a wire with another wire. It's all right-hand rule. Remember, the magnetic field of one wire will have an effect on the second wire, and the magnetic field of that wire will have an effect on the first wire. Please view the Bozeman video on magnetic fields to get a better understanding of that. Remember, I'm still live on Thursdays for you, and you can always email in your questions. You guys are doing a great job so far. I really appreciate the effort. So let's have a great week. And remember, magnetic force law has to do with wires and moving charges in general. Remember, the force of deflection will be the right-hand rule for positive charges, but it will be opposite for negative charges. Remember, our Google Forms are still on Wednesdays and Fridays, and we have those lab simulations. Great job, guys, and keep it up. Really proud of how you're doing. I'll see you next time.